The ground is hot enough to melt a boot. Steam vents through cracks in the rock. The air smells like sulfur. And somewhere beneath the feet of the geologists working this site, an active volcano is still running the same process it has been running for thousands of years. That process is making gold, $8 billion worth of it. Not in a quiet, ancient landscape where the violence is safely locked away in deep time. Not in stable Archean rock that hasn't moved in a billion years. Inside an active volcanic caldera in the Pacific. In a system that is still breathing, still venting, still depositing metal into the rock right now as you watch this video. This is Lihir, and it breaks almost every rule the mining industry built its exploration models around. The volcano isn't the obstacle here. It isn't the risk to be managed or the hazard to be avoided. It is the engine. The same heat making this place dangerous is the same heat that drove gold-carrying fluids through the rock and concentrated one of the largest gold deposits on Earth into a space you could mine. But here is what nobody talks about when they report the discovery number. The deposit isn't finished. The volcano is still running. The gold is still arriving. So what happens when the most valuable thing underground and the most dangerous thing underground are exactly the same thing? Papua New Guinea sits on the edge of the Pacific Ring of Fire. It is one of the most volcanic active regions on Earth, a place where the collision of tectonic plates has been generating earthquakes, eruptions, and hydrothermal systems for millions of years. It is not, by any conventional exploration logic, where you go looking for a mine. Lihir Island is a small volcanic landmass in the Tabar Island chain, roughly 900 kilometers northeast of Port Moresby. From the air, it looks like most other Pacific islands, green, steep, edged with ocean. What it doesn't look like from the air is what it actually is. A partially collapsed volcanic caldera, partially submerged by the sea, still geothermally active, with hydrothermal vents on the seafloor and ground temperatures in places that exceed what standard drilling equipment was designed to handle. Geologists first identified gold anomalies at Lihir in the early 1980s. The geochemical signals were coming from the hydrothermal fluids themselves, the hot, mineral-laden water venting through the volcanic system. Gold concentrations in those fluids were running at levels that did not fit the template for a young, active volcanic system. The numbers suggested something larger was happening beneath the surface than the geology initially implied. What followed was one of the more methodical and technically challenging resource delineation programs in Pacific mining history, drilling into ground that was thermally hostile, managing fluids that were chemically aggressive, building a geological model for a deposit type that the industry had very limited experience with. The resource that emerged from that work sits at over 50 million ounces of gold. It is one of the largest single gold deposits ever identified on Earth, and it exists entirely because a volcano created the right conditions and never stopped running them. Most people picture gold forming the way it looks in old Western movies, veins of shining metal running through quartz waiting to be chipped out of a cliff face. That image isn't entirely wrong, but it skips the part that actually matters. Gold doesn't grow in rock, it arrives there. The process starts deep beneath the surface, where magma releases enormous volumes of superheated fluid as it cools. This fluid, water under pressure so extreme it behaves nothing like the water you'd recognize, travels upward through every available fracture and fault in the surrounding rock. As it moves, it strips metals from the rock it passes through: iron, copper, arsenic, and gold. Dissolved, carried, transported upward through the crust in a slow-moving chemical tide. As those fluids rise, things change, pressure drops, temperature drops. The chemistry that kept the gold dissolved starts to break down. And when that chemistry shifts past a certain point, the gold comes out of solution, it precipitates, it locks into the surrounding rock and stays there. This is the fundamental mechanism behind most of the gold ever mined on Earth. The difference at Lihir is everything that surrounds that mechanism. In ancient, stable geological systems, this process happened millions or billions of years ago and then stopped. The heat source died, The fluids cooled, the system went dark, and what remained was a fossil deposit, the cold record of a process long finished. At Lihir, the heat source never died. The magma beneath the caldera is still present, still generating fluid, still driving that superheated metal-carrying water upward through the fracture network. The hydrothermal system that created the gold deposit is the same hydrothermal system that greeted the first geologists who stepped onto the island. The factory is still running, the gold is still being delivered, and the deposit being mined today is larger than it was 10,000 years ago. Not every active volcano produces gold at this scale. The Pacific Ring of Fire hosts hundreds of volcanically active systems. Most of them will never become mines. The hydrothermal processes running beneath them carry metals, move fluids, and generate heat. But the gold disperses. It spreads through too many fractures, escapes through too many pathways, and never concentrates into grades that make extraction viable. Lihir works because of geometry. When the original volcanic edifice collapsed inward to form the caldera, it created something more valuable than the eruption itself. A structural basin. It contained depression with a specific architecture of ring faults, the circular fracture systems that define the caldera's edges running through it. Those ring faults didn't just record the collapse, they became the plumbing. Pathways that focused hydrothermal fluid flow into predictable concentrated zones rather than letting it bleed outward in every direction. The partial submersion of the caldera added another mechanism entirely, where superheated hydrothermal fluids moving upward through the volcanic system encountered cold seawater pushing inward through the submerged caldera wall. The temperature drop was abrupt and extreme. That thermal shock accelerated gold precipitation dramatically. The interface between volcanic heat and ocean cold became a chemical trap operating continuously in multiple locations across the entire submerged margin of the caldera. This is the combination that most volcanic systems never achieve. The right structural geometry to focus flow, the right thermal contrast to force precipitation, the right ongoing heat source to keep the system running long enough to accumulate meaningful grades. Most gold deposits mined today are fossil systems. The process that created them ended millions of years ago. What remains is the cold record of ancient chemistry, readable, drillable, but finished. Lihir is the live version of that same process. The caldera that collapsed and created the trap is the same caldera being mined today. The ring faults focusing fluid flow are still active. The thermal contrast between hydrothermal fluid and seawater is still generating precipitation events on the submerged caldera wall. The trap was built by a catastrophe, but the gold filling that trap is still arriving. Understanding that the deposit exists is one thing. Deciding to mine it is another conversation entirely. The first engineers who assessed Lihir for commercial extraction encountered a problem set that had no established playbook. Ground temperatures in the ore zone running high enough to damage standard equipment. Geothermal brine, superheated, chemically aggressive, carrying dissolved minerals that would scale and corrode anything they contacted, intersecting mine workings continuously. A hydrothermal system actively trying to flood the pit with the same fluids that built the deposit in the first place. The volcanic system that created the gold had also, in effect, booby-trapped it. The solution required engineering that didn't exist before Lihir demanded it. A geothermal management program was designed specifically for this deposit, one of the most sophisticated ever built into a mining operation. Cold water injection to reduce ground temperatures in active mining areas, brine collection and reinjection systems to manage the hydrothermal fluids without releasing them into the environment, continuous thermal monitoring across the pit to track how the volcanic system was responding to the excavation happening inside it, because that last part matters more than it might seem. Mining a conventional deposit doesn't change the geological system around it in any meaningful way. Mining Lihir does. Removing rock from inside an active caldera alters the pressure distribution in the hydrothermal system. It changes fluid pathways. It affects where the geothermal brines move and how they interact with the pit walls. The operation doesn't just extract from the volcanic system, it negotiates with it. Every blast, every bench excavated, every ton of ore removed is a variable in a thermal and hydrological equation that the volcano is simultaneously solving from its end. What emerged from that negotiation is a mine that runs in genuine partnership with the system it sits inside. The geothermal energy extracted from managing the volcanic heat now powers a significant portion of the operation's electricity needs. The process that had to be managed as a hazard became, over time, a resource in its own right. The volcano built the deposit, and then, reluctantly, it started helping run the mine. Lihir changed a calculation that the global mining industry had been running the same way for generations. The conventional exploration model treated volcanic activity as a disqualifier. Active systems were hazardous. Recently active systems were structurally unstable. Geologically young volcanic terrain hadn't had enough time to concentrate metals into economic grades. The search for gold focused on ancient, quiet, stable geology, the kind of country where the violence was safely historical and the deposits were cold and readable. That model systematically excluded an entire category of terrain. The Western Pacific volcanic arc stretches for thousands of kilometers. It hosts active and recently dormant volcanic systems with structural and thermal characteristics comparable to Lihir. Submarine hydrothermal vents along the same arc are precipitating gold onto the seafloor right now in systems that have never been drilled. The Ring of Fire, treated for most of modern mining history as a geological hazard zone, contains within it the same Caldera geometries, the same ringfault architectures, and the same thermal contrasts that made Lihir work. The question was never whether those systems contained gold. The question was whether anyone was willing to look. Lihir proved the model was incomplete. It demonstrated that a volcanically active, thermally hostile, structurally complex system could host a deposit large enough to sustain one of the most technically demanding mining operations on Earth. That proof is now sitting in the geological literature, in the feasibility studies, in the engineering specifications of every comparable project being evaluated across the Pacific. The exploration, thinking that avoided active volcanic terrain didn't fail because it was careless. It failed because Lihir didn't exist yet as evidence. Now it does. And the regions that were written off as too hot, too young, or too dangerous are being looked at, again, with a different question in mind. The volcano didn't hide the gold. It made it. It concentrated it. It is still delivering it. The only thing standing between that gold and discovery was the assumption that the right place to look was somewhere quieter,